And now we come to additive manufacturing, innovation in materials and processes. And Professor Bill O'Neill, who is the Professor of Laser Engineering at the Institute for Manufacturing, University of Cambridge. And after obtaining a PhD from Imperial College, Bill moved to the University of Liverpool, where he helped to establish one of the world's largest university-based laser research groups. And in 1990, he was appointed Royal Society Research Fellow to study the gas dynamics of laser cutting, resulting in a number of international patents. Bill was later appointed lecturer at the University of Liverpool, where he continued his research on advanced manufacturing systems and technology, in addition to establishing a research base in laser-based rapid production technologies. In 2002, he established a £5 million EPSRC Innovative Manufacturing Research Centre and was appointed to a lectureship in production process within Cambridge University's Engineering Department. He established the Centre for Industrial Photonics in 2006 and continues to research and develop the next generation photonics-based manufacturing solutions. So give a warm welcome to Professor Bill O'Neill.
That was such a nice introduction. I could have written that myself, and had I realised it was going to be voiced word for word, I would have made it a lot shorter. It's also really unnerving when you sat in the beginning of a lecture theatre and you know that the keynote speaker uses half of your slides. Or that the synthetic biologists have such an incredible level of scientific development and opportunity that it makes the material that you might present look rather pedestrian. But that's the position I'm in. I'm going to make the most of it and probably get to you to tea as soon as then you think. How many of you have a 3D printer? How many of you, keep the hands up, how many of you are academics? Okay, how many of you are not academics? Sorry, with 3D printers? Yeah, no hands at all, I thought that. So, you know, this idea about 3D printing, it's pretty astonishing stuff. Let me just get to the right slide. I'm going to talk about additive manufacturing, innovation, materials and processes, and try and pitch it at a level which is understandable and realizable in many respects, and also to try and give you some background to the hype, because there's lots, unfortunately. If we look at 3D printing, actually Phil Dickens is in the room, one of the most eminent 3D printers in the UK. Working down in sort of 1980s, late 80s, the technology spanned through 30 or 40 years or so to get it to 3D printing. It's a de facto term that everyone uses because it's easy to understand. The technology hasn't changed in 30 years. We could have done what we're doing now, 30 years ago, easily, you know, with the technologies, which are slightly more expensive, slightly more demanding of computers, but ultimately what we're seeing is the sudden realization by the press and the media that these machines are available, and it's not necessarily because of the changing technology, it's because of the dying of intellectual property, which allows you to move forward and develop machines. 1 or 2 patents have restricted the growth and implementation of this technology for the past 30 years. Astonishing. Now, is IP a good thing or a bad thing? In this case, I'd say IP is a bad thing, because it's restricted growth and opportunity and application. So be mindful about where this technology comes from and where it sits at the moment. In terms of growth, it's not that big. It's a $3 billion industry. That's peanuts. You know, cardboard box industry is $550 billion per year. Semiconductors, 250, 300 billion per year. This stuff, paperclip money for the aerospace industry, basically. But what is important is that this technology, at this scale, underpins every single product that is made today. It underpins trillions of dollars worth of manufacturing output. So as a scale of industry, it's not very big, but as a scale of impact, it's enormous. And it's essentially, if you look at where the machines are coming from, well, they're mainly American and Israeli because of a couple of really key innovations in that technology within that country take a lot of global sales. In Europe, we have some technologies which are largely German, but they're European for the sake of argument. We have one player in the UK, Renishaw, producing some metal build technologies. So, you know, we're not necessarily pulling our weight in terms of technology and innovation development, but in terms of design and exposure and looking at how some of the technologies that Mark pointed out earlier on about reducing weights, etc., the UK is doing pretty good, particularly with respect to the activities at Loughborough and Nottingham universities in terms of that aspect. So what does this stuff do? Well, if we think about the benefits, it can replace conventional manufacturing processes. We can reduce waste material, always a good thing. We can reduce transport. It brings closer together the user and the producer because they can become one. So you have massive reductions in supply chain and complexity of that, and also the energy used in actually transporting stuff through the supply chain. We can make products far more efficient. Mark showed this example of a light-weighting aerospace component. Only put the material where you want it. If you want a hole over here and a face over here, you can join them whatever type of material you like with this additive processes, because complexity is effectively free. And the process route starts with art to part, and the materials and the machines that you use to consolidate the materials within it give you the defined shape. So it's largely about geometry. The past 30 years have been about form, creating form. And if we look at the trends in the industry, well, we can see the low-cost 3D printers. So these things are running at, if I can find my laser pointer. Yeah. These things here are running at several $100s. Technology, as I said, hasn't changed for decades, but it's become capable of delivering usable machines. We can develop very complex features. So the low-cost 3D printers have increased visibility. They've increased the user access and capabilities in some respects, and have supported the craft-based activity of the industrial sector. We can see now these are all the components for the first 3D printed gun, the Liberator. Strange name for a Terminator. But anyway, it's plastic components. The only metal component is this thing here. It's a nail, and you can buy that from B&Q, or in America, I can't remember what the name of the equivalent for the American B&Q is. Home Depot. Thank you, Americans. Home Depot. So incredibly, before this data was taken off the web, 1.5 million downloads occurred. So there are 1.5 million potential gun makers sitting furiously with their 3D printers like this, because most of the machines have been made on this stuff. I mean, these are more likely to explode with this technology. And this is the firing of the weapon. It's a University of Texas law student who's really taking on the system by designing this very first gun. The first test, it blew up. The second test, it worked, and he decided to take the third test bravely, and fortunately for him, it worked. But what it's done is set the scene of really worrying law enforcers all over the world for various reasons. I'm sure you can summarize them yourself. What it's done is allowed designers and manufacturers to extend their capabilities and to think about complex components and shapes which they couldn't do with conventional processes. It's really allowed the development of high-performance polymers as well, because not all of these materials that are used in these machines are normal materials. They're taken to a point where they have to have slightly different properties to perform. So in terms of the machines, I'm not going to go into detail. The stuff on the web, we basically can summarize the way in which you consolidate the material, either by using powder beds that you melt or glue together, or vats which you photopolymerize with lasers, or extrusion machines like cake icing makers, jetting with 3D printers, or binder jetting where you spit glue onto a powder framework, or sheet lamination where you join bits together. So very traditional approaches to the creation of form, and the machines range from millions of pounds to a few £100s. They range from resolutions which take you down to a few microns to a few hundred microns. And you can really select your material and your specification, your design to really meet. If you want to make a real gun, by the way, you're really going to have to use this technology. It's a couple of £100,000 worth. So there's a sort of a natural prevention of all this spillover of capability. But these things are getting cheaper and cheaper. And in fact, in my group, we're producing one which will be sub £5,000. I'm not quite sure how you can stop people making guns with these things. It's very difficult. Data management? Who knows? Alarm bells ringing, or just embedded intelligence which prevents you from doing stuff that they shouldn't be doing. Anyway, that's not a problem for the material scientist. The actual process, for those of you who don't know, is very simple. Take an object, slice it up like an inverse of a bacon slicer. Slice, slice, build, and we consolidate layer by layer by layer by layer by layer all of the material in one way or the other as described by the previous techniques to produce said part with complex internal geometry, very nice features, things you couldn't make without tools, things you couldn't make without massive overhead in production. can be spat off these machines willy-nilly. In terms of the applications, Mark, this one was a great shot. Thanks very much. I nearly died when I saw that picture. I thought, my God, next he's going to show a guitar, and then he's going to show, jewelry. All of these things that really are important to individuals, because it's not so much the applications in prototyping, which is why the technique was developed and really used 30 years ago, or tooling. People don't care about that stuff. I don't care how the thing is made. I want to buy the thing. And when people were asked, what would you do with a 3D printer, they all said, what? What would I do with a 3D printer? Is it going to make my goods cheaper and more accessible? Then fine, let the professionals make the stuff. I just want to use this stuff. There's quite an interesting discussion about where this stuff will fit en masse. But what we can see is that, apart from all of these guys who have been using them for decades, we've started to see whole industries built around new ways of making particular products, not least of which is those products in the medical sector, where we're seeing surgical models being routinely applied in the US because, you know what? It saves money. The insurance companies demand that these technologies are used in the US to reduce patient residency time, to reduce the complexity of operations, and to guarantee a more successful outcome from an operational procedure. So interesting sectors which are specific to the individual are really taking a real boost from some of the innovations in this area and establishing huge developments which we're starting to see across the world. This is the world's largest, you probably can't see it down there at the back, this is the world's largest 3D printed aerospace component from China, and these guys plan to fly this next year. The parts that were shown earlier on for aerospace, that's a very sensitive industry. They're not necessarily going to fly a million spot welds, because that's effectively what some of these parts are. So it's going to take a long time for the aerospace sector to get confident in this technology to move it forward. But certainly things like tooling and the other areas we've already heard about, biocompatible materials, have shown great promise. So the range of applications is huge, and the impact potential, despite the very small capital value of this industry, is huge also. So if we look at the application share where it sits for boring data, but very interesting in some respects, aerospace 10%, they don't make many airplanes per year. Tooling costs money. If you can reduce costs on tooling and non-critical components, then you'll grow the parts to put in your aeroplanes. Medical and dental sector, huge growth in this area. Vast majority of metal implants now within the framework of your mouth are made by additive manufacturing. Huge industries across Europe and in the US making tailored parts for you at no cost. You wouldn't see that. It's an invisible process to you. Invisalign fixtures, orthodontic fixtures, invisible in the sense of transparent plastics, but they're not, the production chain is invisible to the user. They don't really care. They get the benefit of a good fit, a good function, and a good process. Consumer electronics, we're starting to see some of these innovations have been used not as direct parts, but as supporting the design and development process. If we start to look at the materials, because after all we're talking about materials, we can pretty much do anything you like, even ceramics and glasses these days. And we have the processes which give you conventional materials with conventional properties, and that's pretty dull on the whole. This is a super, super sexy technology capable of putting stuff where you want it, when you want it, in the precise volume, repetitively, day after day after day, and all we're doing really is producing form. Now that's great for certain industries and certain materials, and we can even do things like, apart from the usual engineering materials, things like elastomers, and this is a polyjet process from Objet, which is a pretty neat inkjet printing system which prints two types of materials, an elastomer and a polymeric material, where you can start to produce multifunctional components. Very good for the transfer of design or marketing information. Not necessarily so practical. I'm not saying that these things would last very long at all, but they're simulations of the kind of materials that we use in conventional industry. But nonetheless, we start to see, well, some of these technologies can be driven towards printing an iPhone or printing an iPad, rather than having it made in these huge factories, $10 billion operations in the Far East, rather than made locally by your local print shop or your local provider. We've also got things like PEEK, a replacement for some of the medical device alloys, titanium alloys. Very good biocompatibility. It's lightweight. It's a good biopolymer. It's been used or has been tested. Now, it's not been FDA approved, but it's starting to be sought and developed. And if we look at things like titanium, Chris Sutcliffe and his team at Liverpool University, Peter Goodhue is here, I think, have seen amazing developments. Probably one of the world's leading research groups in developing biocompatible titanium-based implants. And these are going to be bespoke technologies, and this sector will argue within 10 years, 80% of the biomedical implants will be made by additive manufacturing. It's just more cost effective. It gives you greater performance and capability. Not only can you make structures which the bone grows into, you can make structures which have a varying degree of stiffness. So you can get metal systems to behave like bone and perform like a biomaterial, even though it's a fairly straightforward transplant. In terms of biomaterials, again, the synthetic biology talk gave a good example of that. We're seeing bioplotters or bioprinters printing scaffolds around which cells are seeded and produce various types of materials from fibrin and collagen and gelatin, etc., where we can see things being developed across a whole host of technologies. And the very early one was an EnvisionTech machine, which is basically a Cartesian robot with a needle spitting out material over 3 dimensions. So technologically, the delivery systems are very simple. What's really important is the materials. It's the materials that empower these technologies to do something more than just a traditional manufacturing development. And the materials challenge for us and for the researchers in this community is not the machine, it's the materials that go into the machine. But it's the way in which we can think about materials. If I have control over the way a material is processed, deposited, formulated, very much like the synthetic biology outputs where you engineer intelligence into a system, we can actually start to design the specification of the material that we want. We can then start to have feedback and see exactly how we should approach not only the material's composition, but the way in which it's manipulated. And that will give us opportunities to develop new materials. So we have to go beyond form, as we have done for 30 years, and move towards function and form, because that's really where the power of this technology sits. And just to give you a couple of examples before I finish, we're seeing British Aerospace start to develop deposition systems for wing structures, where we're growing aeroframe components. The problem with the most growth of metals, if you're a metallurgist, you'll know, is the microstructure. You don't want a cast microstructure particularly, where you cool from the outside in. And this process is you're cooling from the layer bottom up. And so by changing the experience of the metal, you can actually produce microstructural changes where you can engineer crystalline features to give you control over elongation or stress or flexibility. My team here have just produced some nano-exchange coupled supermagnets, where we've built the material from the inside out, producing a collection of nano, hard and soft magnetic phases to reduce rare earth consumption by 90% and increase the magnetic strength of the material. Now, if we can do that, the battery innovations can be waited for, because if you improve the magnetic material, you automatically increase the efficiency of your electric system. And so by being able to design the material microstructure and selectively add it, we're able to produce some major innovations which will hopefully see vast improvements in electrical performance of every device, whether it's power gen, power delivery, or energy harvesting. Another example here is where we're no longer melting material. We can deliver material in a solid state form at super high speeds and consolidate one metal that just wouldn't sit next to another simply because of a metallurgical incompatibility, and deliver nanoscale structures, where we've talked before about the importance of nano. Nano is just as important in terms of bulk objects as it is very small objects. And here's an example of a nano grain surface stellite 6 material, which was deposited using the new SLD technology, an additive technology, which reduces the coefficient of friction by 50%. Same material, same composition, just the way it's delivered has engineered new solutions. So this is where I see the big opportunity in additive fabrication, not just shape or form and plastic or metals, but thinking about the nature of your material and seeing how you can re-engineer and reconfigure it to produce a challenging transformation. So in summary, it's clear these technologies are going to grow and become more and more capable as our awareness increases. This thinking beyond form towards function is essential, not just shape, it's capability of the material. We have some amazing developments in the EPSRC funded initiatives. The Sim and Additive Manufacturing Phil Center in Nottingham and Loughborough, I think, are involved in that too, who are producing new technologies to create functional objects, i.e. multi-material electronic mechanical systems. So moving towards printing an iPhone or printing an iPod. No more chess pieces or repairing washing machine components. We're talking something a little bit more sexy and having distributed factories potentially rather than these big centralized monoliths that produce silicon or iPhones. And my centre in Ultra Precision, which is working on sub-100 nanometer additive manufacturing capability, trying to get to the bottom of some of the details of nanoscale features, but for macro competency, macro capability. And the TSB Innovate program is supporting that up the TRL level. Worthwhile pointing out that we're going through a spending review at the moment, and if you know any politicians, are there any in the room? They're never a politician when you want one, are they? To think about not cutting our EPSEC budget by the 10% which has been proposed, to think about putting money into the manufacturing and the wealth creating enterprises in the UK, and that includes all sciences, not just those involved directly in manufacturing. We're seeing printed, so that's the political bit over. The printed electronics is now a reality. Samsung are printing TVs. There's one machine in Korea that can print 1.5 million TVs per year. Why would you want to roll up your TV? I never quite figured that one out. But anyway, we need to establish, and this is really the important thing. We talked about schools. You've all been in industry where you've had, in schools where you've made something. Think about what you made when you were a school kid. G-clamps, table clamps, a chain link remover, I don't know, Black & Decker workbench if you went to a really good school, or something of really that's you can remember making, a tangible thing that you produced and you walked home with to show your parents. I'm not sure we do that in schools anymore. And I take Mark's point about bringing together lots of the disciplines that need to produce creative wealth creators and innovators and designers. We're not doing it. We're going to lose this race if we don't do it. So we need to establish this technology across the primary and secondary sector. In the old days, every school had a suite of Colchester lathes, made in Colchester, run by technicians who were proud of them, all gone practically because of one reason or another. But we need to just regain our position in the education system. It's no good, to quote a former Tory leader, it's no good if some of you won't be here in 40 years' time, worrying about the future. It's the next generation of engineers and students that we need to do. And the Royal Academy has got to be part of this to try and deliver it. And I think that's it, actually. One more point. This could be the next output from your Christmas party. So, thanks very much. I'm sorry I've overrun.
Not at all. Well, thank you very much.